Okay, thank you. Then let's go ahead and move to the next slide. So Caleb Fassett, yesterday I already gave you a very good talk on some specific applications of MinRef data for Artemis landing zone characterization. I'm going to zoom out a little bit, give a higher level view before maybe showing a few Artemis zone scale things with a slightly different flavor. So first we'll talk about the instrument itself. MinRef is a hybrid polarized synthetic aperture radar. It's dual frequency at both S-band and XC band. That's 12.6 centimeters at S-band and 4.2 centimeters at XC band. It is operated in both a monostatic mode, and that's where the transmitter and receiver are co-located. And when the transmitter failed on MinRef, we started working as a bistatic system where we transmitted from ground stations here on Earth and received at the spacecraft. In that monostatic mode, it could operate in a 2-bit or 12-bit mode with a fixed look angle. So we could use compressed or uncompressed data. In bistatic, we use only compressed data, 3-bit, at a variety of look angles. And this is so that we can get into the configurations we need to collect data. So for that monostatic phase, as I mentioned, the transmitter failed after a couple of years in flight. It vastly outlived its lifetime, but we used MinRef a lot more than we thought we would initially. So from 2010 to 2012, we operated in monostatic. In 2013, we transitioned to bistatic mode and are continuing to collect bistatic data through today. Spatially, with the monostatic data, when it's compressed, we get down to about 30 meters. That's resolution. Caleb mentioned yesterday we can get down to 15 meters. That's more pixel scale, but you can learn valuable things at that scale. At our uncompressed, we're at 150 meters. We're more sensitive, but we have lower resolution. And at bistatic, we're at 100 meters. And as a reminder, we have a penetration depth associated with our observations, and it's linked to the wavelength at which we're transmitting and the dielectric properties of the material we're observing. Next slide, please. Again, kind of at a high level, what can radar provide? What does it do? It gives you wavelength scale information on the distribution of scatterers within the penetration depth of the transmitted signal. And so the cartoon here on the right showing a variety of scatters at a variety of sizes and several radar wavelengths that are penetrating the surface to different depths and that are sensitive to different scatterers. So each in and of themselves can provide very valuable information on the distribution of those scatterers or the bulk dielectric properties of the regolith that they're transmitting into. But really a combination of those wavelengths can really be powerful for understanding properties of the surface and near subsurface. Now for MinRef, we're XC and S-band. There's another radar in orbit around the moon, which is active and collecting data. That's the DFSAR instrument on Chandrayaan-2. It has an L-band frequency and also S-band, so it overlaps with us. One other really important thing to point out is we have access to PSRs with our monostatic data and to some extent with our bistatic. For monostatic, shadow-free, we are our own illumination source, so we can see into permanent shadow. The bistatic, we are limited by the visibility of the ground station and what it can see, which is sometimes different than what the sun would see. So we can occasionally see into permanent shadow. Next slide. This is just to give you a little sense of what kind of coverage we have with MinRef over Artemis zones. So in the top right, this is S-band compressed, so our highest resolution coverage. And as you can see, we cover most of the pole and most of the Artemis zones at that frequency. For X-band in the lower right, in purple, it's most of our coverage comes in the higher sensitive 12-bit mode, which is lower resolution, but still has very good coverage of the pole and a number of the Artemis zones. Next slide, please. When you add in the bistatic data, we cover a lot of the holes in that coverage. Now, when we cover those with bistatic, that doesn't always mean we're seeing into permanent shadow. So there can still be some areas that weren't covered by monostatic that we cannot observe because they're permanent shadow. But we still do get very good coverage at both wavelengths for much of the Artemis zones. Next slide, please. Caleb showed this image in his talk yesterday. I'm showing it again just to remind people of a few things. We can see differences in radar reflectivity, and this is a map of that for those polar data that I was showing, normalized to a consistent incidence angle to mitigate the effects of local slope. And you can see variations, and these variations at high levels should reflect changes or differences in regolith properties. And there are some interesting things to see here. There are some variations. For instance, and Caleb pointed out that Mons Mouton has low radar reflectivity, and on the other hand, Faustini, which I'll show later, has high radar reflectivity in S1. And more broadly, you see Hayworth, Shoemaker, and Faustini and Amundsen craters. They all have high S1 reflectivity, while Cabeus has low, right? So we see variations, and I think as we've been describing over the last couple of days, context is important. We want to be mapping these interesting Artemis zones, but we also want to understand their context to help us map them as good as we possibly can. Next slide. Caleb pointed out the ray from Tycho that covers Hayworth, and you can see it in these S1, this delta S1 data. Next slide. But there are other products we can produce with our radar data that can pull out specific things of interest. This is another look at that polar data, but now we're looking at it in opposite sense polarization. So we're taking a couple of our Stokes parameters and using it to help us isolate the width of the Tycho ray as it comes over the pole. And so you can see in this inset that dashed box is the Hayworth Artemis zone, and we can point out both the width and the asymmetric ejecta associated with the secondary craters, and hopefully more effectively map those for that zone for consideration in operations. Next slide. Caleb also showed CPR, I believe, yesterday. And this is another way of looking at roughness of the surface. This is a relative roughness. And there are differences here when you look at this compared to that radar reflectivity product, that S1 product we showed. One important one that was pointed out by Caleb was Mons Mouton has a low S1 reflectivity, but a high CPR, which has some implications for regolith properties. As a counterexample, that Faustini crater region had a high, a high S1 radar reflectivity, but has low, at least background CPR. And when you zoom in on it, you can see while there's a fresh crater that has high CPR, indicating high roughness elements associated with its ejecta, the background terrain is relatively low CPR. So this has different implications for regolith properties, and is something to note when you're mapping this region and comparing it potentially to Mons Mouton.
90 seconds.
Yeah. And I'm almost finished. Next slide. And this is really my last slide. And what I wanted to point out is that we have radar coverage, radar data for all of the Artemis zones and at multiple wavelengths for the vast majority of them. MinRF cannot collect any more S-band data, or at least can't currently in bistatic operations, and we cannot collect X or S-band data in monostatic mode anymore. But at S-band and L-band, the DFSAR instrument can collect data, and we can provide requests to them for areas of interest, and the pole is an area of interest for them. So we can continue to utilize MinRF data, we can collect new bistatic X-band data with MinRF, and we can look at leveraging DFSAR in orbit around the moon to get additional data for Artemis zones. And I would contend these are very useful data for characterizing landing sites and science operations in these regions. And with that, I'll finish.